So from central limit theorem, sampling distribution of the sample mean, or x bar, has the following parameters. The first one is that the mean of the x bars, the population mean, mu of x stands for the population. Let's write that down so we don't forget that real quick. I don't know. Mu of x is equal to the population. We call the population mean. X bar is called the sample mean. So mu of x is the population mean. X bar is called the sample mean. If we try to read this here, mu of x bar, what does that mu stand for again? Population mean. What does x bar stand for? The population. So the population mean of all the sample means. We did an activity for this, but the population of all the sample means is equal to the population mean. That's significant because I can find samples with no problem. It's a lot harder to find a population value. You have to know all the values in the population to do that. So what does this say? Instead of trying to find the population value, I can just take a whole bunch of samples, find their average, it'll give me the population average. And it also says this, and it also says that, bless you, bless you, the standard deviation of x bar, where sigma x is the population standard deviation. Sigma x is the population standard deviation. It's equal to sigma x over the square root of n. And we call this value the standard error. The standard error is really the standard deviation. The problem with calling it standard deviation, though, is that what is this value called right here? The population what? We can't call this value the standard deviation again because we have the standard deviation divided by what now? The square root of a sample size. Everybody got that? So we give it a special name, which is called the standard error. But the standard error is just a standard deviation. You got that? Yeah.
Wait, standard error is just what?
The standard deviation. I didn't mean to do that. I'll bring it back. That's on me. I was trying to delete the other thing. Hey, why does this all matter? Well, to y'all it doesn't matter because you don't really remember anything about central limit theorem. The big thing about central limit theorem is this. When things are normal, that's what I care about. I'm trying to make things normal, which means they fit a normal curve. Well, what happened to my thing?
Wait, does S
Where'd it go?
What the heck?
This is weird. This is trippy. All right. So here's what's the most important thing then. The reason this all matters is because this distribution is going to follow an approximate normal distribution. An approximately normal distribution. That's why this matters. But it does that when the sample sizes are sufficiently large, or we say sufficiently large when n is bigger than what number? Do y'all remember? Nobody remembers the number. Say it again.
30.
Thank you. Hayden is 30. Appreciate that, Hayden. Thanks. So when it's bigger than 30, it follows an approximate normal distribution. And that matters now because of this. If it follows a normal distribution, we talked about these things called critical values. What kind of critical values have we talked about? What do we call the critical value? Do you remember? Come on, man. Somebody remember what we call a critical value? We did this all last chapter with the proportion.
P hat, Q hat.
What else? P hat, Q hat, what else?
Z star.
Z star. We want to talk about some Z stars, all right? That's what we're talking about now, so. Here's what's going to happen, though. In order to talk about Z star, here's what needs to happen. The standard deviation. The standard deviation, which we call, what do we call the standard deviation again?
Standard error.
What do we call the standard deviation though? That's right. That's close. What do we call it?
It's the,
What symbol is this?
Sigma.
Sigma. If sigma is known or assumed to be known, if the standard deviation of the population or the population standard deviation is known or assumed to be known, we can use the z critical value. So we're going to use, if the standard deviation of the population is known or assumed to be known, we use to create an interval based on the z critical value. The z critical value is also called z star. Do y'all remember how to find z star? How? What function do we use in our calculator? Inverse norm. Thank you. So remember, we use the inverse norm function. So we can use inverse norm to find the z star. So here's what I mean by it has to be known or assumed to be known. And it has to meet certain conditions. N has to be bigger than 30 is one of the conditions it has to meet, all right? Because when n is bigger than 30, what happens? The distribution is approximately what? Normal, which lets you use the z value, all right? So look here. A simple random sample of 21 Chihuahua dogs weight yields a sample mean of 5.6 pounds. It is known that the standard deviation of the population of all Chihuahua weights is 1.8 pounds and the distribution of weights is normal. So here's how this works. The first thing you do is identify two things. The first thing I want to identify is, do I know the mean value? Do I know the standard deviation, the population standard deviation?
Yes.
So either they're going to tell me that or they're not going to tell me that. Do they tell me I know it, yes or no? Is it known?
Yes.
Yes. Where does it say that at?
1.9.
It says that, right here it says, that it is known that the standard deviation of the population of all Chihuahua weights is 1.8 pounds. Everybody got that?
Yes.
So we're going to write that out. So we know that sigma, which is the standard deviation of the population, is 1.8. Y'all okay with that?
Yes.
Standard deviation of the population is 1.8. The other thing I need to know is this. I want to look at the sample size. And the sample size has to be bigger than what number? 30. So I want to know what is n equal to. Well, look here. What is your n equal to? Tells you how many you're looking at. A random sample of 21 Chihuahuas, right? What's wrong with that number? It's less than 30. Now, here's what can happen. Then there's one condition where we can still use this. Does anybody remember what that condition is? If it's less than 30, what else could we do? Yes, if it tells you it's normal. Do they tell us it's normal already? Yes. It tells the distribution of weights is normal. So because of that, we can actually use a z star. Does everybody understand that? We can actually use a z star. And here's what happens. This distribution has a mean, mu of x bar equal to the mean of the population, which is, what's the mean of the population? Try it again, it's standard deviation. What's the mean of the population? 5.6. And the standard error now, which is sigma of x bar. Listen, the standard error, which is sigma of x bar, that's equal to the standard deviation of the population. What's that? What's the standard deviation of the population? 1.8. But you have to do what to that number? Divided by the square root of? 21. Good. So 1.8 divided by the square root of 21 is equal to this number right here. So this is approximately 0.393. So you get this new value called the standard error that you need to calculate. That's going to be the standard deviation for the actual sample itself. Look at the next one. An automobile manufacturer believes that the average mileage per gallon of one of its new models exceeds the mean Environmental Protection Agency rating of 43 miles per gallon. The sample mean and standard deviation for the 144 cars were 43.6 and 1.3 miles per gallon respectively. So first thing, do we know the standard deviation, yes or no? Yes, what is it?
1.3.
Thank you. 1.3. Do we have a sample? What's our sample size? The sample mean and standard deviation for the 144 cars. So your n is equal to what number? 144. What's significant about that number? It's bigger than what number? 30. So here's what we write. Mu of x bar is equal to the mean of the population. What's the mean of the population? 43.6. Sigma x bar. It's the standard error for the population, or the standard error for the sample. What's the standard deviation of the sample? Or what's the standard deviation of the population? 1.3. And we're going to divide that by the square root of what? 144. So we do that. 1.3 divided by the square root of, what's the square root of 144? Well, you get this number right here. 0.108. Everybody okay with that? So far, so to make the interval, here's what happens. Administrators of an urban hospital examine the gestation times of babies born at the hospital. Does everybody know what gestation time is? Y'all know what gestation is? What is it? It's how long a person is pregnant for. It's pregnancy. You got that? It's just pregnancy, all right? The director of the birthing center at the hospital selected a random sample of 25 babies born at the hospital in the previous 6 months and recorded the gestation time of each baby. The mean gestation time was found to be 267 days. Human gestation times for healthy pregnancies are thought to be accurately described by a normal distribution with a mean of 280 days and a standard deviation of 14 days. Find the 90% confidence interval for the true mean gestation time of babies born at this hospital in the last 6 months. So first thing, we want to identify two things. Is a standard deviation given to me, yes or no? Do I know sigma? Look at it again. Yes. What is sigma x equal to? Thank you. They tell me standard deviation is 14 days. What's n? What's n? 25. Thanks, Casey. 25. What's wrong with that number?
Less than 30.
It's less than 30. So what do I do next? Check to see if they tell me that it's what?
Normal.
Do they tell me it's normal? Yes. Described by normal distribution. So I'm okay with that, everybody. Got that? Now, in order to create the interval, let's go back to proportions. How do we create an interval for a proportion? What do we do? What came first in a proportion? Y'all remember? How do you make the interval for a proportion? What came first? What did you take first in a proportion? Y'all don't remember the p hat? Y'all remember p hat? Plus or minus what? What came next? P hat plus or minus e. What is e? What was e equal to though? P hat plus or minus what?
Q.
No. Come on. P hat plus or minus. No.
The
Z star. Thank you. Somebody said it. Z star. P hat plus or minus Z star times the square root of what? P hat, Q hat over n. Where this right here is the standard error of p hat. This is the standard error for p hat. And Z star is the what? What do we call Z star?
That's the common.
That's the critical value. This is what we call the critical value. That's the critical value. Together they make up the what? What do we call those when you multiply them together? Somebody said it earlier. You multiply the critical value by the standard error, what do you get? E, which is also called the what? Margin of error. Good. So these make up the margin of error, E. Does everybody understand that? Well, for a mean, it's the exact same thing except things are going to change because you're not talking about proportions. A mean and a proportion are similar, but proportions means you're taking it out of the whole. It's part to whole. A mean is a measurement, is an average measurement. So when you do that, here's how this looks. The new interval you're going to create looks like this. Instead of talking about pi, you're talking about x bar. What does x bar stand for? What does x bar stand for? X bar is the, what kind of mean? Sample mean. Thank you. X bar is the sample mean. So we have x bar plus or minus. You're going to take a critical value. The critical value here again is going to be z star times the standard error. What's the standard error for x bar? What's the standard error for x bar? X bar is called the what again? Sample mean. Plus or minus, what does z star stand for? Critical value. Times the standard error. What's your standard error here for x bar? Sigma x over the square root of n. That's why we've been finding that value, by the way. Sigma x over the square root of n. So here we go. In this problem, here's what you're looking for. You need a mean. Did they give me a mean, a sample mean? They actually give me two means, by the way. What are the two means they give me? They give me a mean of 260. The mean gestation time was found to be 267 days for a sample, right? For a sample of 25 people. They also give me the population mean, which is what?
280.
280 days. Which one of those am I going to use for X bar? 267 or 280?
280. 267.
Why 267?
Because you need the population mean for the mean.
You need the actual, not the population mean, you need the, what kind of mean? What kind of mean do you want to go? What does X bar stand for again? So what kind of mean do you want? The sample mean, right? This 267 comes from the 25 women. Does everybody understand that? This 280 is the actual true mean. We understand that? Or what it's thought to be. So here, we're going to go first. 267. Plus or minus. How do you find Z star for 90%? Y'all remember? Yes, inverse norm 0.95. How do we do that? Let's do it again. Let's draw it out. Draw a curve. On the inside of the curve is what percentage? On the inside of the curve, what percentage?
90.
90%. How much is on the outside?
5.
5 to both sides, right?
0.95 and inverse.
So this is 5%. This is 5%. Remember, we're adding up to this value right here, right? So we do inverse norm. Yes. Inverse norm 0.95, and we get a Z star equal to what? 1.645. So it's 267 plus or minus 1.645. What does that represent? That 1.645 is the what? Critical value. Times the standard error. How do I find the standard error? Thank you. 14 divided by square root of 25. What's that?
When I do, how many what away?
So here we have 14 divided by square root of 25, which is going to be 14. What's square root of 25? 5. So this will just be 14 divided by 5, which is that, 2.8, times 1.645. So the margin of error here is what? What's the margin of error?
4.607.
Thank you. So we'll write it like that. We'll do 267 plus or minus 4.606. Now what are we going to do? We're going to add that value and subtract that value. Everybody got that? So 267 minus 4.606. The lower bound, 262.394. How do I find the upper bound?
Add it.
Add it now. 267 plus 4.606. 271.606. Yeah, got that? Okay, so we add and subtract the margin of error. That gives us that answer. I want y'all to try example 2. Example 2, a simple random sample 36 St. Bernard dog weights yields a sample mean of 193 pounds. It is known that the standard deviation of population of all St. Bernard dogs weights is 18 pounds. Find a confidence interval for the true mean weight of all St. Bernard dogs with 99% confidence level. So here, do we know do we know sigma x, yes or no?
Yes.
What is it?
18.
Sigma x is 18. Do we know the sample size?
Yes.
Which is?
36.
And 36 is bigger than what number?
30.
30. Hey, so listen, 36 is bigger than 30 means I can use the normal curve here. All right. What is X bar?
193.
Thank you. The sample mean, they tell me the sample mean is sitting right here at 193. The other thing I need to actually write the interval is going to be Z star, right?
Yes.
Z star 99%. Here's how we do it. Draw a curve. On the inside is what percentage again?
99.
So the inside is 0.99. How much is on the outside then?
0.5.
0.5% to both sides. Which means I'm going to do inverse norm of what?
0.995.
0.995. And I get a Z star equal to? Yes, 2.576. Is it 576 or 756? 576, round up. Now, to create the interval, what goes first?
193.
Thank you. So we do 193
Plus or minus 2.576.
plus or minus 2.576 times the standard deviation, which is 18 over the square root of 36. So z star times the standard deviation over the square root of n. What's 18 divided by square root of 36? What's the square root of 36? 6. What's 18 divided by 6? 3. So you just do 2.576 times 3. That means that this value over here is 7.728. So you're going to add that and subtract it. So 193 plus 193 minus 7.728.
Is that important to do like the minus first?
Yeah, because this is lower bound.
The lowest bound to the highest bound.
Thank you. Good job, Angel. 185.272 is the lower bound. 193 plus 7.728. That was a great question, Casey, by the way. Thanks for asking. Hey, make sure you write the lower bound first and the upper bound next. 200.728 is the upper bound.